Okay. Well, hi everyone. Hope you're having a great day today. We're going to go over chapter 11.5, which is power and roots of complex numbers. So this will kind of answer your questions about why do we do this and what is the purpose of a complex plane. So you get a visual representation of what does it mean when we try to find complex roots, and how is it useful or more useful that we see this in trig form or polar form rather than in rectangular coordinates. And you will see that in rectangular coordinate we cannot see these complex roots. So let's get to it. So power of complex numbers. So last time we kind of talked about how to multiply two complex numbers together in trig form. And we do that by just multiplying the values of the r, and we are adding the angles together, right? So if I have r1 times r2, you would just take r1 times r2. But since here we are taking a power, so essentially they are the same r and the same angle. So here we see a formula for r cosine theta plus I sine theta squared. So this is the second power. You can see here that we raise this to the second, and this is also 2 because we have 2 theta, because we are multiplying two complex numbers, but they are essentially the same complex number. So in the same way, similarly, you can see here that if I take it to the third power, then we raise it to the third, and here the n value is 3. So therefore, in general, if I take it to any nth power, and we raise r to the n, and then we take n times theta. So in shorthand notation, this is the first formula that you should memorize for this theorem. For this section, which is called the De Moivre's theorem. Later on, you see that we're also going to look at how to approach this when we're dealing with roots as well. So very similar process when we go to the roots. Okay, so let's look at the power of a complex numbers. Here we are looking at the 8th power. So we're trying to take 1 plus I square root of 3 to the 8th power, and we can do this by rewriting this into a trig form. And to let's review how to do this. So 1 and square root of 3 will basically be your x and your y. You can think of it like that. Since they're both positive, we know that it's going to be in the first quadrant. This is x, this is y. So to find r, just use the Pythagorean theorem. Square root of 3 square plus 1 square. Square root of that will give you square root of 4, which is 2. Okay, so this is basically a 30-60-degree triangle, where this one is 30 and this here is 60. So therefore, you can see that theta is equals to 60 degree. My r value here is 2. So to write it in trig form, we have r cis theta, and theta here is 60, r is 2. So to raise that to the 8th power, all you do is take 2 to the 8th, and then 8 times the angle. So here we have 256 cosine of 480, and we try to get the coterminal angle. And to do that, we just have to subtract 360 degree until you get to a number that's between 0 and 360. So here we get a cosine of 120. And of course, we can evaluate this to put it back into rectangular form, or you can rewrite this in shorthand notation, 256 CIS 120. So this is in polar form. This here, we're trying to convert it into rectangular form. So we evaluate cosine of 120. So since cosine 120 is in the second degree, second quadrant, we see that it equals to negative 1/2. And it is positive for sine, so we have square root of 3 over 2. And then you can distribute each one of these to have the rectangular form of this, which is the same thing as 256 CIS 120 in polar form. Everything good so far? Okay, so now we're going to talk about the nth root, which is basically going backward. Okay, so if you look here, we know that negative 128 plus 128i square root of 3 is the 8th power of this. So this means that if I take the 8th root of this, I will get 1 plus I square of 3. Okay? So now we're basically just going backward. So this is what it's saying right here. For a positive integer n, the complex number a plus bi is the nth complex number if x plus yi is this. So if I take it to the 8th power and it equals to this, that means that the a plus bi is the 8th root of x plus yi by going backward, right? So here we're just going backward by setting it up just like we did over here. So to find the complex root of this complex number, we're going to set up the following. R cosine alpha plus I sine alpha to the 3rd power is equals to this. So basically, we started off just like this over here. Okay, we don't know what the value in here is. That's what we're trying to find. But we know that if I raise that values to the 3rd power, I'm going to get this over here.
So the 3rd power because we saw that 8 could be cubed.
No, they asked us to find the cube root.
Oh, they asked us. Okay.
Yeah, that's a request there. The 3rd is equals to 8 by this formula over here, right? By De Moivre's theorem. And we also know that 3 times theta equals to 135, right? So therefore, we can find out what theta is. Well, this is very easy to solve, right? So very simple to solve for this. So r here is 2, and r here is 45. Okay. So here you can see here how they set this up. So we know that r cubed cosine 3 theta is equals to this. So we set the r cubed equals to 8, 3 alpha equals to 135. Okay. So the 3 alpha here, let's look at how they set this up. So to solve for alpha, we basically just divide the following. Now notice that we have to do 360 k because we need to find out all of the possible angle or possible roots that will give us the roots for the complex number. So let's review a little bit of college algebra before I explain what this is. So the fundamental theorem of algebra states the following. Polynomial of degree n, there exists n complex roots. Okay, so what does that mean? Let's say I have a function that looks like this. So here, my degree is equals to 2. So degree is the highest exponent of a polynomial. So here our degree is 2. So we expect to have 2 complex roots. Now in college algebra, you are known to find this by understanding this as an x-intercept or zeros, which means that when the y value is equal to 0. But in pre-calculus and calculus, we don't really call it x-intercept or zeros anymore. We call them roots. The reason why we call this roots is the following. Suppose that we have a quadratic here. We just have passes -10, it opens up. So here we are guaranteed to have 2 x-intercept or zeros. Now what happened when I actually have a something like this? So here we do not have any zeros or x-intercept because you can see here this parabola does not cross the x-intercept of the x-axis. So this is where we have 2 complex roots. So a root is a solution to the equation, but it is not an x-intercept. So that's why we call that a root. Also, you are expected to have two of them, okay? Because we have a quadratic here. So this is probably x squared plus something. I don't know, I'm just going to make up something. So let's say this graph here is this, okay? So this does not have a solution. So therefore, we are going to look at what does it mean when I graph these complex roots for a parabola like this. Now over here, we're looking at cube root. Okay, so cube root is going to be similar to what we have here, but you will notice that we have three different solutions. Okay, so this is basically just the inverse of the fundamental theorem of algebra, where here it asks us to have the nth degree. Here, the degree here is 2. We expect to have 2 roots. So here they're asking us to find the cube root, which we expect to have 3 of the roots. Okay, so cube root means you're going to have 3. Square root, you have 2 solutions. Fourth root, fifth root, eighth root, whatever. How many roots there are, right? Is how many solutions you're going to have between 0 and 360 degree. So now when you are trying to find these type of solutions here, it's a lot easier to understand how these arrive rather than trying to use this formula here. So I'll show you both ways, and you can choose to learn it either way. You can choose to learn it either using the formula, which is basically just 360k, and then divide by whatever how many roots there are. So here in this case is 3. So you are expected to have 3 roots before it starts rooting again. So if you keep going, k equals 3, 4, 5, 6, 7, whatever, you're going to get these values again, which co-terminate with these angles. So we only have 3 unique solutions or roots, and then after that, it's going to start repeating again. So let's see what these 3 roots represent and what they look like. Okay, let me erase this here. All right, so first of all, I'm going to see if we can graph this. Now, this is on a complex plane, so this is I, and this is the real number line. All right, so the first one is at 45 degrees. So here we go, 45 degree. And I believe my R value was 2. So this is the first one. And then after that is 165 degree, so somewhere over here. Also 2. And 285, which is a little bit more than 270, over here. All right, so this is 45, 165, 285. Now let me ask you this, just visually, what do you see here with the relationship between these 3 roots? Visually, what do you see? Do you recognize any similarity between them or something with a relationship between them? Maybe the angle between them?
I think they divide 2 pi into thirds.
Exactly. Means you are taking 360 degree divided by 3 even spacing between roots. Okay.
So I mean, if you extrapolate that, right, any nth number of roots, does it always divide it evenly? But does it always divide 360 degrees evenly?
Exactly. So you can see here, you're taking 360, you're dividing by how many roots there are. Okay, so you can understand the formula here, and I just demonstrate to you that when you sketch it, that's exactly what it means. So this is a visual representation of what that formula is. And you can see all that here. See? Okay. So if you want to understand using the formula, the number of roots is the number of k value that you're going to use, not when k is equals to that root. So here, since we want the third root, we want to use 3k, and k always starts at 0. So we use 1, 2, 3 values of k, not k equals to 3. Just like we did before when we solved for equations. Right? Okay. So that means that if you can find the first value of the angle here, you can definitely find out the rest of these very easily by just dividing it by how many roots there are, and then just adding that. Okay. Now all three of these numbers are complex numbers because notice that they are in the complex plane. Any number along this x-axis will become a real number. Okay. So let me demonstrate this and see if you understand this. If I have I square, I'm sorry, x. So this one will help you understand it. X squared equals to 1. What is the solution to this?
Plus minus 1.
Plus minus 1. All right, so I take square root on both sides, plus minus 1. Right? Now, how would I graph this on a complex plane? This is I, this is where. Where does it go?
It's going to go x-axis. So on the real number axis, on the 1 and -1 marks.
Right, so here and here, that's my two solutions. You will notice that they are evenly spaced, right? They are 180-degree difference between the two of them, right? Right. Let's look x to the 4th equals to plus or minus, oops, equals 1. Now what?
Oh. It's also, gosh, is it? Let's see. It's also plus minus 1, isn't it?
Yeah. Well, here we're taking the 4th root. So minus 1. So here's the thing. There's only 2 here, right? We are expected to have how many?
4.
4. Right. So where's the other 2? So we know that 2 of the solution is 1 and -1, but where is the other 2? Where do you think it is?
So are they on the imaginary axis?
Yeah, so let's see if this is true, right? So this is positive 1i, this is negative 1i. So you're saying that I, negative 1, and 1 are solution to this here. Well, let's see if that's true. What is I?
I squared is -1. -1 times -1 is +1. So, well, that's I cubed. And then +1 times I would be I. So it's I, right?
No.
Okay, oops. So
I squared times I squared. I squared is -1. -1 times -1 is 1.
Okay.
Okay? Negative I. What's -5 to the 4th?
Negative I squared is still going to be, shoot, I mean, because you squared, right? It's
Yeah, negative I to the 4th is the same thing as I to the 4th because this is a negative. Negative to a even power is just positive, so you get. Does that make sense now? We have 4 solutions. They are evenly spaced by 90 degrees. Okay, and I just show you that when you take it to the fourth power of I, you get 1. Is that cool?
I'm kind of confused as to why you took I to the fourth power when you were trying to explain why X had 4 solutions. Can you go over that slowly, please?
Okay, so there are 4 solutions. I am just plugging it in to test it out. I'm checking the answers.
Oh, you're plugging in. Okay.
So
And then
here
you
I'm plugging in I. Here I'm plugging in negative I. Of course, if I plug in negative 1, that's obvious, right?
Okay, I see.
See it? All right, so you see we do have 4 roots for this. Only think there's 2 because we only deal with real values in college algebra. We don't really touch complex numbers all that much. Okay, so now you can see here we have 4 solutions and they are evenly spaced between 0 and 360. Okay. Okay. So here's the answer. It's just putting everything together here. We just find the nth root. We take the nth root of r cosine alpha plus I sine alpha. Okay. So ideally, I suggest you just set it up like you did before up here, like this. Once you set it up like this, it will become very obvious just to apply De Mor's theorem. And you can choose to memorize this if you want, but if you understand how to get the first one, the rest of them will follow. But here, let me explain. Theta divided by n, and then 360 divided by n give you your spacing. So you just keep going until you have that many roots. I'll give you a minute to try this. Find the 2 square root of 4i. So square root means you're going to have 2 of them. So set it up. First, we write the 4i in trig form, and then apply De Mor's theorem. Need more time or hint or comment?
I think I got it.
You got it?
I think so, yes.
Mm-hmm.
I will have a modulus of 4, so r equals 4. The theta, because it's on the quadrantal of the imaginary axis, would be 90 degrees. So in writing it, we can write 4 CIS 90 degrees squared. 2 as the, we'll call it power. We have r squared CIS n theta, or 4 squared CIS 2 times 180, or 2 times 90. So you get 16 CIS 180 degrees.
Very good. Okay, so let's look at the solution here. So first we write the 4i in trig form. So here, just like Aim was saying, 4i is in the imaginary axis because this is a positive 4i. Okay, so it will be right here. 4i would be right here. So therefore, the r value will be 4. The angle is from here to here, 90 degrees. So we have cosine pi over 2 plus I sine pi over 2. So we can set it up because we want the square roots. So we want to use a plus bi. R here, choose the square power equals to this here. Okay, so we know that r squared equals to 4, so therefore r is equals to 2. So we got that. Okay, and then for the angle, we know that the angle's pi over 2. We have to multiply 2 times our theta is going to equals to pi over 2. So therefore, see what we got over here. Except our first one was at. Okay. So our first angle is pi over 4. Now, let's see, we can draw that here. This is pi over 4. This is our first one. And since we only have 2 roots, the other one will be directly opposite from there, which means that the angle here is 180 degrees. So if this is pi over 4, this would be 5 pi over 4 over here. So that gives us our 2 angle. And then from there, we know that the r value, what is the r value equals to? And we can rewrite this in rectangular form by finding out what is my x and my y value here, or my a and my b value here is. Okay, so this is nothing more than a 45 degree triangle. Okay, so we have our sides here be square root of 2 and square root of 2. Therefore, in rectangular form, you have positive square root of 2 plus square root of 2i, and negative square root of 2 minus I square root of 2 because it's in the third quadrant. Okay. Let's try again. Here we are asked to find the fourth root. How many did you get the last problem? Okay.
Yeah, I got it.
Okay, great. Okay, so let's see where is negative 8 plus 8i squared of 3 is. So first, let's draw our triangle and sketch it out to give you an idea of where it is, and that will help us find our modulus and also our angle. So negative 8 and 8 square of 3, that's just like your point x, y. This is negative, this is positive, so we know that's in quadrant 2. So from here, we can find out what is my r is equals to. So square root of 8 square of 3 square plus negative 8 square. So that's going to be 16. And my angle here, now you can use tangent of theta is equals to opposite over adjacent. The 8 will cancel, so negative square of 3. So this is going to give you 60 degrees, and that means that my angle theta here is 120 degrees. Okay, so now we got our r value, we got our theta value. We can rewrite this as r CIS theta 16 CIS 120. And so we can find out what is the root is. What root do we want here? The fourth root. So we want r CIS theta raised to the 4 is equal to this. So now we can set it up the equation. R to the 4 is equal to 16, and n times theta is equal to 120. So r here is equal to 2, and n here is, let's see, what is our n? 4. One of them will have a difference of 90 degrees, so I can extend this out here to give you the other one, and also perpendicular to this because it's 90 degrees. So here is one, here is one, so that's 30 degrees. 30 plus 90, 120 plus another 90, 210 plus another 90, 300 degrees. So that gives me the 4 angle that I need in order to write out all 4 of my roots. So the solution is x is equals to 2 CIS 30, that's the first one, 2 CIS 120, 2 CIS 210, and 2 CIS 300. So there you go. So we have 4 roots of the original problem, which was what, 8, I don't remember what it is, negative 8 plus 8i square root of 3. So there we go. Now, of course, you can convert this back to rectangular form if you'd like. Any question? There you go.
Hey, Professor.
Yes.
When you drew that last graph, right, and when you drew those right triangles, it got me to thinking, would all the roots be, if you consider the roots as vectors, would all the roots be orthogonal to its other roots?
Yes. Yes, it is, but only for fourth root.
Only for fourth roots. Okay, got it.
Yeah, because they differ by 90 degrees. Okay, and of course you can convert them to rectangular form. So if you forgot how to do that, 2 cosine, for example, 30, the first one, plus I sine of 30. So here you just evaluate cosine of 30, that's square root of 3 over 2. Sine 30 is 1/2, distribute the 2. So square root of 3 plus I, that's your first one right here. Okay? And you can do the same thing for the other ones. So it's very important that you memorize all of the special angle here to get this quicker. You can see here the graph of what it looks like, which I drew earlier. All right, go ahead and do this example. Now we're talking about the fifth root. Do we need more time, or are we done?
I'm not done yet. Not yet, sir.
Okay, just post the answer when you're done. Okay, well, let's look at this now. So first we try to solve it by setting it equals to 1. Then we'll take the fifth root on each one. So the first one of them is at 1. So we know that if I try to take the fifth root, okay, of each side, now this is a fifth root, so you don't really have to add plus or minus 1. So I know that the solution is x equals 1. Where's the other 4? Well, I told you that all of them are evenly spaced between 0 and 360. So if you draw your number line, where this is your I and this is your real, so let's say this is 1 right here. So this is our first solution. The rest of them will be divided into 5 evenly spaced. So we have 1, 2, 3, 4, 5. Wait, is that 5? No, it's not 5. Oh, this is one right here. Okay, so 1, 2, 3, 4, 5. So now we can take 360, divide that by 5. We get 72, I think.
Yes, that's what I got.
All right, so 72 degrees between each one of them. So all I'm going to do is take, because I know the first one is on the real axis right here, so that's at 0 degree. So 0 degree, 72, and then keep adding 72. So 144. And then 72, 200, 16, and another 72, 288. 1, 2, 3, 4, 5. There we go. So that's 5 of them. $144. And there you go. That's it. You don't have to do so much work. I was wondering why you guys are taking so long.
Professor, when you have so I wrote the equation instead of 1 CIS 0 degrees, I wrote it as 360 because when I set up R times A plus BI to the fifth, it was easier for me to calculate it that way to get 72 because 5n equals 360 degrees. Okay.
Of course. All right, so you can see here, we got 0, 72, 144, 216, and 288. And of course, the R would be 1 because the distance right from here to here is 1. It's already on a real axis, so you don't really have to solve for anything. You can see here the 5 different roots. They are evenly spaced, 72 degrees from each other, and with a modulus of 1. All right, that wraps up this one. So you can ask homework question now.
All right, let me go grab the homework. Oh, before we do that, right? So I got all 5 angles, 0 through 288. Once I have that, right? For the formal solution set, I always have to enter those angles into this the rectangular form, right? So 1 CIS 0 degrees.
Whatever they ask you, because sometimes they just want you to write it in polar form, or they want you to write it in rectangular form.
Okay. So my first question is going to be on homework 11.4. Question 0.47. So let me see what question number that is. Question 15 out of 22.
Okay, let's see. 11.4. Number 16?
Number 15. And for me, the equation was to write the complex number in trig form, and the complex number was negative 2 root 2 plus 2 root 2i.
Okay.
My question was, after I was trying to find the angle, right?
Say the complex number again? You have 2 root 2 and what?
2 root 2i.
2 root 2i. Okay.
Here's where I got confused. I kind of like rationalized it out, but I knew the two sides of the triangle which that length or which that created, and so I set up the tangent of theta equals 2 root 2 over negative 2 root 2, which got me negative 1. I took the inverse tangent of negative 1, and that got me negative 45 degrees. But
Yeah.
I was confused because I thought negative 45 degrees would be in quadrant 4, not quadrant 2. So I mean, I knew that theta was 135, but I didn't know what to do with that negative 45.
Okay. So let me explain why that is. So you know that negative 2 root 2 and positive 2 square root of 2 is in quadrant 2, right? So negative 2 square root of 2, 2 square root of 2. By the way, if these two are the same, this is 45 degrees. That's
Yeah,
given.
I mean,
Okay.
yes.
Now you are trying to do tangent of theta is equals to 2 square root of 2 over negative 2 square root of 2. Then to solve for theta, you did what? Tangent inverse of 2 square root of 2 and negative 2 square root of 2, which is tangent inverse of negative 1. Now, let me ask you this. Whenever you're doing tangent inverse, what
I
is
see
the
what you're saying.
domain?
I see
Range
what
of
you're saying.
tangent inverse?
Yeah,
It's
the
only
1
1 over
and
4.
4. Yeah.
This, you are using reference angle of this. Okay? You are trying to solve for a reference angle. So anytime that you're doing this, I don't suggest you actually write in this right here. You should just do it using the triangle without referencing to the quadrant. So you just use positive values for everything. Then once you know what this angle is, then you just reference it to the correct angle, to the correct quadrant. Because if you do that, it doesn't matter what quadrant you're in. Like if you can draw your triangle in any other quadrants, so you can do 2 square of 2 here, negative 2 square of 2 here. But if you only use the positive value, you know that this angle here is 45 degrees. But you put that together with the quadrant that you're in the fourth quadrant. So what you need to do to get this angle here, take 360 minus this.
Yeah, I think that's how I rationalized it.
So
Yes.
this should be reference angle, and the angle you're trying to find is theta. So this 45 here is like reference angle.
Okay. I get that. Okay, so the next one would be in homework 11.3, part 3. Let me pull that up, and it's going to be question 111. So 11.3, part 3. Question 111 was, let's see.
Mohammed, do you have any homework question?
109, 111. Okay.
No, I
You good? Okay.
So my issue here is that I didn't understand the symbols that they were using when they were trying to when they were trying to define volume. Volume equals R dot A. So I understand the dot product. Question three, sir.
Mhm.
So I'm not sure if they were trying to find the magnitude of R dot A or the absolute value in this case of R dot A.
That's magnitude.
That's magnitude. Okay. Okay. And I mean, this seems almost like a calculus problem, isn't it? In a way?
Let me see.
Not necessarily.
No, it's not.
Okay. So I mean, so now I understand that it was volume is defined by the magnitude of the dot products of R and A. My last question for this one was that why is volume in cubic inches rather than squared inches? Is it because one of the variables was in inches squared and one of the other one
Yeah.
was in just inches?
Yes. Yeah. So when you are multiplying, you need to also multiply the unit. So I mean, for example, if you're looking at volume of a cube, the formula to find the volume of any type of prism is length times width times height. Say that's height right here. Let's say that's width. Each one of them, let's say, have a unit of centimeters. So you take length times width times height. You're also multiplying centimeter times centimeter times centimeters, so you get centimeters cubed for volume.
Got it. Yes, sir. I understand that. Okay, so I mean that answers that question. The last one that I had was in homework 11.3 part 2. Let me pull that up. It's going to be number 81. So yes, I want to leave. And this is one of the bearing ones, right? And I got it wrong initially. I had to redraw it just because I didn't understand the terminology. I think I do now, but I just wanted to get a confirmation from you, sir. Let's see, it is number 80. Why am I not going here? Part 2. To number 81. Let's see what that is. Let's see. Oh,
2 is about magnitude and directions of vectors.
okay, hold up. I think I got the numbers wrong. 73105. What is that in? I apologize. It might be in part 3 now, sir. I apologize for that. Yes, I want to leave. Oh my god, it won't let me leave the homework. Okay, part 3, 105. Here you go. So it's number 1, part 3.
Okay.
So the issue on hand here is that when they use the word he wants his flight path to be on a bearing, I had an issue with that because I got the I drew the angle wrong initially, and I just wanted to see how I wanted to see how it should be how that sentence could be should be considered.
Okay. So let's see. I'll read the problem I have here. So a pilot is flying at 172 miles per hour. He wants his flight path to be on a bearing of 44 degrees in 30 minutes. So that's his final uh, bearing. So that's where he wants the airplane to fly. Okay. So well, the question asked is, if there's a wind that's blowing from the south that's 34.7 miles per hour, find the bearing he should fly at. So which means that what should he set his airplane bearing at so that his final bearing is 44 degrees and 30 minutes.
Got
Does that
it.
make
And
sense?
then that final bearing is the bearing that's affected by the wind, right?
Yes. So his flight path is the one that's already affected by the wind. So if you set the airplane in one direction, the wind is going to blow it to a whatever drift angle it is, and then that's going to be your final flight path.
Okay. Okay. I think I get that now. There was one more wind one. 225 degrees. So I feel like these vector ones, when it has to do with bearings, are the more complicated ones that I've seen so far in the homework issues, the homework. So I'm thinking those would be the more complicated ones on the test as well. Can you clarify when it says the wind is coming from the south? We assume that it's going to, the vector direction is going to go up north, right?
Yes.
Okay.
Yeah, the
Now,
head is going to point north.
Now, when it doesn't use those specific words, but they say that the wind is from 200 degrees or 225 degrees, right? Where is the head going in that direction?
In the opposite direction. So if there's a word called from, so here on number 2, it says the wind is blowing from the direction of 186 degree. So find out where 186 is. Let me find it. So we're talking about bearing. So it's always going to be due north. So 186 degree would be down here, right? a little bit more than 180. Now this is where it's coming from, so it's actually going to be this direction here. So just draw a straight line, okay, and then this is where it's going.
Got it. And then I seem to remember from your lectures, and then it's emphasized in the homework as well too. Basically, when you're doing these kinds of problems, it's essential for you to understand the I forgot if it's a trapezoidal rule or whatever, so that you can find the angles correctly for the triangles that are created. Is that true?
The parallelogram.
Parallelogram, that's the one, yeah. So, I mean, I understand that the corners are supplementary to each other.
Yes, these two are supplementary.
hmm And then by doing that, right, you could basically find all of the other corners. I remember.
It's not always that easy. Some of them are easy, but when you're talking about a wind blowing at an angle that's not north or south, you can't really use the north or south pole in order to help you find the angle. You actually have to do some geometry there.
Yeah, you have to create a transversal line somehow, right?
Yes. Yes.
Got it. Yeah, I remember that concept as well too.
Yeah,
One
you
of the
use the wind as your traversal and then your north and south line as your parallel lines.
Oh, okay.
Yeah.
Okay, that makes a lot of sense. To reiterate one of the rules of the parallelogram, that dotted line that you wrote out, that you drew out in the parallelogram, that doesn't always necessarily bisect the angles, right? The resultant.
No, I mean, it almost never bisect the angle. It bisects bisect each other. Like this and this is the same. This and this is the same.
Got
It
it.
bisects the diagonal. It does not bisect the angle.
Okay.
Yeah, the only time it bisects the angle is when you have a square.
Got it. I think it's not the most difficult one, but the one that required the most finagling and drawing out of new uh, triangles for me was when you had to find out the amount of force that there was a box on a slope, and you had to find out how much force is required to keep that box on the slope.
Mm-hmm.
So that was number 89. Let's see if that was the second to last one. I think that was
Yeah,
number
so
6.
you're looking at the normal force, the weight, and then the force required to keep them all up. So all three of these are going to create a triangle. So we're going to move this one right here. We'll move it down. So let me see if I can try to do that. There you go. I'm going to move this down here. And then I'm going to move this piece right here. Down here. Now, ideally, they will be the same length.
And I mean, so I had to read the text a little bit to understand it more, but the vector that is orthogonal to the slope, right? Um, that is that represents the force that the box is exerting onto the slope.
Yes, they call that the normal force.
The normal force. Okay. And I mean, we assume here with the different movement of when the rearranging of the vectors, that it creates a right angle.
Yes. Just like I draw here. Are you looking at the screen?
I am, yes. And the assumption that the right angle was created is because it was a right angle when it was at the box, right?
What do you mean?
So before you move that down, the that vector. Let me go to the whiteboard and see if I can draw it so you can understand why I'm saying that. I'll do it in green. We assumed we'll call it was right here, and that was a right angle, right?
Yes,
So when
that's
you
a
moved it
normal
down,
force.
yeah. So when you
By
moved it down,
definition, the normal force is always perpendicular to the surface. And you
oh,
can see here the force that we push is also the same plane as the ground. So therefore, that's where the 90 degree comes from.
got it.
So this is the normal force. This is the actual force that you're pushing.
Okay, and then the last part. So I didn't do it this way, but I kind of get why you're doing it. The theta in the red triangle is it's equivalent to the theta in the blue triangle.
Yeah.
Can you explain why?
Yeah. So if you look at the slope here, now we know that this is going to be 90 degrees from here to here, right? Because this is the normal force, right? So, and this is 90 degrees here because the weight is going down, right? So whatever this value is, this is 90 degree minus theta, right?
Yes.
Agree?
Agree.
So, but you also have 90 degree right here. Okay. So yeah, it comes over. So if this is 90 minus theta, it means that this part right here have to be theta because you also have 90 degree right here.
Got it. Okay, I see.
Yeah.
That made it so much easier. Basically, I took the 90 degrees from the right triangle created by the weight and then added that to theta, and I subtracted 180 from that amount to get 90 minus theta.
Yeah, you get the same thing. Mm-hmm.
Yeah, I mean, I was just trying to understand why the book was explaining it that way, but yours was a clear explanation. Okay. All right. I know you have the test review out already, so I'll be reviewing that as well too. I see that you've kind of changed the way that the test reviews look like. Is there some kind of like hint or cheat code that you'd like us to focus on the test reviews now?
Cheat code.
Yeah, I mean, like it's a really detailed test review, Sarah's. I think it's much more detailed than the last two. So I'm just trying to figure out why you made it so much more detailed, because is the test going to be that much harder?
Yeah.
Of course.
So all these test reviews I've made before. So this is test review that I've made probably 2 years ago.
Oh.
Yeah, so this is for, and normally exam 3 is the hardest one, and I want to say the average is probably very low. For exam 3, that's every single semester because the material is a lot harder. You have a lot more formulas to memorize. You have stuff that's compounded, so you will have more formulas to use to do the proofing. And of course, these bearing problems are not that easy. The one thing that you will not have that you can omit that I did not get a chance to take out is the three-dimensional. So you do not have to sketch three-dimensionals vectors. So that metric graphing, you can ignore that.
Okay. So then, number 15.
And also the page number on the bottom there, I think that's for the older edition of the book. So yeah, you can probably ignore that too.
Yes, sir. Number 15 for me, I think it was interesting because you gave a three-dimensional array, right? It has three.
Mm-hmm. Yeah, but you do it exactly the same way as two-dimensional.
Okay.
Yeah.
Yeah, I kind of remember that now.
Whatever the formula is for two-dimensional, you just apply to three-dimensional. And I mean, any higher dimension is still the same thing.
Got it. Is there a difference between 15C and 15D, where 15C is the dot product of two vectors that should yield a scalar, while 15D is the addition of two magnitudes, right? So the addition of two magnitudes,
it's also a scalar value.
It's also a scalar value. So with the addition, is it still A plus C and B plus D?
Oh, that's dot product.
That's dot product. Okay, so I have to review D.
So the magnitude just does Pythagorean theorem, A squared plus B squared. Since if it's three-dimensional, you can do plus C squared and square root of all that.
Okay, got it. Let's see. So Heron's theorem. Okay, I see Heron's theorem as well too. That was pretty clear. No, I don't have any questions.
Just plug and check on that one.
Yeah, I have no issues with
But make sure you review all the different types of triangle properties, like side angle side, and all that stuff.
Okay.
And when to use law of sine, when to use law of cosine.
I see. I see. And then one of the things that I really liked about your lectures earlier on in this section was basically you talked about the swing of an ambiguous side of an ambiguous triangle, right? And the swing would allow us to define whether there's one or two triangles, right?
Zero triangle, yeah.
Or zero triangles. And that swing is basically an analytic comparison between the side which we're not sure if it defines a triangle, the height of the triangle, and then the known side of a triangle, right?
Yeah.
Okay. Now, my question from way, way back, I just remembered now. If all three sides of a triangle are defined, then there's no swing, right? Because the sides are already defined?
Exactly.
Got it. That made a lot of sense because I was trying to figure out why I was trying to define the swing when all three sides were already defined.
Yeah. Well, I mean, that's why there are congruent triangle for side, 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 but not congruent triangle for angle, angle, angle. There is no such similar attributes or properties for angle, angle, angle because you have similar triangle, not congruent triangle. Because you can have two different size triangle with the same angle but not the same size. So we cannot call them congruent.
Okay. And I think I emailed you once on one of the homework problems about just like rounding errors, and I followed your advice, and I just like stored all the variables, all the derived answers, all the derived sides or angles in a variable. But my concern is going forward with the test, right? Since we won't have access to our handheld calculators, I'm afraid that I'm going to get all these rounding errors once we go back to class calc because we can't.
So when you have that, you should type in the values for it rather than typing in and then pressing enter. So your final answer, you should be able to type in the entire thing, not necessarily the number. So for example, if your answer require you to do like theta is equals to 3 sine of 42 degrees over sine of 56 degrees, you should type all this in. You should not type sine 42 equals blah, 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 sine 56 equals blah, 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 and then use these numbers. Don't do that. Type in the whole thing, where there is no rounding, no estimating number whatsoever. And then, only then, you should round off this final value. That's what I meant here.
I see. I understand now.
Yeah.
Okay. So on some of the review, I guess we haven't reached that yet because that may be 11.5. So I'll ask that when that comes. I don't seem to remember a lot of definitions or identities for this section. So as long as we understand how things were derived, law of sines, law of cosines, I think we should be able to get that. As long as we understand the difference between a dot product and the difference between a vector addition, we should understand. Oh, the quotient, the vector quotient one took me forever to get last night. Let's see. The last one in 11.4. So 11.4, last problem. Yes, please. 11.4, last problem. And what I tried to do initially, oh, not last problem, I apologize. 65, 69, 65, there we go. So, I mean, it had some arbitrary complex number on top and some arbitrary complex number on bottom. What I tried to do is I tried to multiply it by the by its conjugate, right?
Oh, no. Okay, so to find the quotient, you just divide the R value and then subtract the angle.
Yeah, okay.
Yeah, because if you multiply, you would multiply the R value, but then you add the angle, right? This is just a law of sine cosine.
All right. Okay. Yeah. So in the lecture then, like I know that we covered, I wrote down to divide a complex number in rectangular form, multiply complex conjugative denominator.
Right.
I don't think I saw that in the homework, sir. Can we like and I haven't.
Well, you can come up with anything. So you can just give me two complex numbers and we can do it.
Okay, cool. Let me get some paper as well too.
And 2 minus 7i divided by 4 plus 5i. There you go.
Okay. So 2 minus 7i, 4 plus 5i. Now the key to multiplying a complex conjugate is that the numerator will always yield a real number, right?
No, denominator is always the real number.
Denominator, okay. So then we're going to multiply by 4 minus 5i, 4
Right.
minus 5i, and that's going to be 16 plus 25. 16 plus 25 on the bottom, right? Yes. 16 minus that. 5i squared, negative 5i squared, that's positive 25. Okay. And then the top is going to be a it's going to be a complex quadratic, right? So it's going to be
Any complex quadratic, just for them.
7i squared. Okay, yeah. 8, 10i, 28i plus 35i squared. So 8 minus 28i minus 35 over 30, 41. Yep. Okay. 38i. Okay. Over 40. Okay. So that last step is because we want to keep it in a plus bi form, rectangular form.
Yes.
Got it.
Yeah. So this is your A. This is your B.
Okay.
So this includes the negative as well.
Okay, I see what you mean.
So this means that your x and y value, when you're trying to graph this, negative 27 over 41, negative 38 over 41, which means it's in quadrant 3.
Oh, okay, yeah, I see what you mean. I thought that a plus bi form always has to be a plus. You're writing it as a minus bi?
That doesn't matter. I mean,
Okay. Because I mean,
yeah, you can plus a negative number. That's the same thing.
yes, sir. Okay. All right, and so that's it for my questions for the homework. Thank you, sir, for taking the time. For 11.5, are we expecting 11.5? Okay, so then to remind myself, 11.5 next time, then next week, 1 day of review on Tuesday. So I should have all the test review done and be ready for questions on Tuesday, correct?
Mhm.
Okay, and then after Tuesday, on Thursday, no test review. We're just going to go on to the section that will be covered in the next test.
1. Yeah, 8.1.
Okay, cool. Thank you, sir. I appreciate your time.
Yeah. Yeah. We also have 11.7, but I think we can forego that.
Is 11.7 important? Calculus?
Parametric equations.
Okay, these are words that I don't know yet, but will that be covered in the final though?
No.
Okay, not covered in final.
I don't think it would be. Was it in the syllabus? I don't think it's in the syllabus, is it? I put 11.7 in there. I don't think so.
I have it in my syllabus, sir. It is covered
Yeah.
more parametric equations.
Yeah. Okay, then maybe we have to cover that then. All right. Well, that would be back to regular then. Back to regular schedule then.
Okay, I understand.
We'll do 11.7 next week. 11.6 on Thursday.
Yes, sir. And then, I mean, I hate to be that guy who does this to a class, but whatever. 11.7 is not listed on the homework assignments. Will you be adding that on, sir?
Yes.
Understand. Thank you, sir.
It's not going to be a huge part. Maybe it'll have 1 problem or 2 problems, but it's not a big part of the test. I just
Yes,
want
sir.
to introduce it because you will see that in calculus.
Cool. Well, parametric equations, is that also somehow involved in statistics as well?
No.
No. Okay. Like for me, right, my entire life is based on statistics and linear algebra right now, so I'm just trying to get my head around it.
Parametric equation is just another way to write an equation that involves a third variable. Usually it's time. So normally in Cartesian coordinates, you have something like this where you have a parabola. That's the function. But if you have something like this, that's not a function because then it doesn't pass the vertical line test. But in here, we can actually use parametric equation to graph this and be able to give a position in relative to time. So I can say that a particle is moving along this path.
Okay.
At a specific point in time, let's say t equals 3 seconds. Where is the particle? Well, we can say that the particle starts here at 0, 1 second, 2 seconds, 3 seconds. So we can say after 3 seconds, it is here. So it add on another variable other than just x and y. We call that the t for parametric variable, and that is normally represented by using time. So we know the time that the particle is at a specific point.
Cool.
So that's what we use it for. Yeah.
Very cool. Will that be on our test review as well too? Because I know you said the test review was from 2 years ago. So does that already cover parametric?
I'll have to add. Yeah, I'll have to add that to it.
Okay. All right. Hey, Professor, thanks so much.
Yeah, on Thursday.
Thank you, sir. I appreciate your time.
Thank you.
You have a good one.
Take care. Bye bye.